Welcome to Pure 3 integration. In your earlier studies, integration was introduced as the simple reverse process of differentiation. You added 1 to the power and divided. But the mathematical models that describe the real world, from the continuous decay of radioactive isotopes to the oscillating currents in electrical circuits, are rarely simple polynomials. Pure 3 integration blows the doors off that foundational concept. It equips you with a sophisticated toolkit to integrate almost any standard mathematical function. The challenge here is no longer just the integration itself, but rather the recognition of the function. You must look at a complex expression and instantly identify the correct mathematical tool to unravel it. Our journey begins by expanding your library of standard forms and identities. First, you will learn how to integrate exponential functions, which are essential for modeling continuous compounding growth or decay. Then we move to standard trigonometric functions, integrating basic periodic and cyclical functions like sine, cosine, and secant squared. But examiners will rarely give you these standard forms directly. You will frequently face squared trigonometric functions like sine squared x. You cannot integrate these directly using a basic power rule. Instead, you will learn to deploy double angle and Pythagorean identities to manipulate these expressions into standard forms that you actually can integrate.
Next, we tackle the heavy lifters of the pure mathematics syllabus, substitution and parts. What happens when you have a complex composite function? You will use integration by substitution. This technique allows you to unravel the chain rule by temporarily swapping variables, turning an impossible-looking integral into a basic polynomial. But what if you have a product of two completely different types of functions, like an algebraic term multiplied by a trigonometric term? For that, you will use integration by parts. You will learn how to choose which function to differentiate and which to integrate, reversing the product rule to solve high-tariff exam questions. Sometimes, the secret to integration is pure algebraic manipulation. When faced with complex algebraic fractions, standard calculus rules will often fail you. In these cases, you will use the method of partial fractions. This technique bridges pure algebra and pure calculus. You will use algebraic long division and decomposition to break a massive, complex rational expression into a sum of simple, bite-sized fractions. Once the algebra is done, the actual integration is straightforward. A-star candidates stand out here by their algebraic stamina, ensuring they do not drop negative signs or forget the constant of integration.
Finally, what do we do when an exact analytical integral is mathematically impossible? We abandon exact algebraic formulas and turn to numerical methods. The trapezium rule estimates the area under a curve by slicing it into straight-edged trapezia. You will calculate these approximations by finding the area of each shape. Crucially, examiners will ask you to analyze the concavity of the curve. If a curve is concave up, a straight line connecting 2 points on the curve will sit above it, proving your numerical result is an overestimate. You will need to justify this in your exam.
Integration in Pure 3 is a high-stakes puzzle that carries heavy marks. You must know your formulas, but more importantly, you must develop a strategic approach to problem solving. You are now ready to begin.